Let's look at another example of a differential equation, which we'll solve using separation of variables. And let's also sketch the slope field. So let's first sketch the slope field. Now remember, in this case, the derivative is in terms of not just the y-coordinate, but the x and the y-coordinate. So that means we're going to have to consider both points when we're actually plugging points into this differential equation. What I recommend though is look for some obvious points or some obvious values of the derivative. So for instance, if x is 0, then you're dividing by 0 here, so the derivative would be undefined. So any place where x is 0, the derivative should be undefined. And what that means is you can't really indicate anything. So the entire y-axis is when x is 0. So I'm not going to indicate anything there because you can't, right? There's no slope. On the other hand, when y is 0, when y equals 0, the derivative is 0 because you have 0 in the numerator there. Now so that means I'm going to put horizontal lines to indicate a slope of 0 at these places. Notice I didn't do it at 0, 0 because that happens to be also where x is 0, and that's where the derivative is undefined. Okay, let's actually plug in a few particular points. Let's do dy dx. Let's plug in the point 1, 1. When you do that, you get 1 over 1, which is 1. So we need to indicate a slope of 1 here. So now be a little bit thoughtful. If I plug in 2, 2, the same thing should happen, so that should have a similar slope. If I plug in -1, -1, same thing should happen. You should get 1, and as well as -2, -2. So we just basically found that entire line without actually plugging in each individual point, and that's an important thing to do, or to be able to do. Let's try looking at the point 1, -1. When you plug in 1, -1, you get -1 over 1, which is -1. So that gives you this shape here, or that slope there. But then, of course, if you plug in 2, -2, you'll get the same thing. -1, 1, similarly. All right, so now we see our slope field starting to take some shape. Now, what I like to do at this point is you can continue plugging in some more points if that makes you comfortable. But one thing I like to do is I'll look at some of the rows here. So this is the row y equals 1. This is y equals 2. This is y equals -1. Y equals -2. We'll say this is x equals 1, x equals 2, x equals 3. So what I'll do is look for patterns. And I'll note, for instance, if we go across, so let's go to the point 1, 1. If I'm going across the row, the y-coordinate is not changing, right? So the y is staying fixed. However, the x-coordinate is growing. If the x-coordinate is growing, if you look at your differential equation, that means the denominator is growing, even though the numerator is staying constant. So that means that your slopes are getting smaller. And so you don't need to be, it's impossible to get a perfect slope, so all you need to do is indicate that these slopes are getting smaller. So I'm going to make them less steep as we move over to the right there. All right, and the same thing will be true up here on the top row, right? This, as x goes, as y equals 2, at the line y equals 2, the numerator is going to stay as a 2, but as you move to the right, it should be getting less steep because the x-coordinate is getting bigger, which means if you move to the left, it's getting more steep. All right, that's a better way, I think, of viewing this problem. I'm going to kind of just finish this up here. I'm going to have you can check this on your own, but it should generally, this slope field should look something like this. Again, details aren't the most, I mean, the details don't have to be perfect, but you need to get a sense of what the shape of these functions are going to be. It's a little too steep. Alright, so there's a decent slope field. Now let's go actually find the functions that are associated with this slope field. So we're going to use separation of variables. So we're going to use separation of variables. to solve this differential equation. So if you cross multiply and then divide, you can get this to look like dy over y equals dx over x. And now we take the antiderivative of both sides. So the antiderivative of 1 over y with respect to y is the natural log of the absolute value of y. And the antiderivative of dx of 1 over x with respect to x is the natural log of the absolute value of x. Both of them would have a plus c, but you can just group that on one side here. Now we use the definition of log. So that means e to the ln of absolute value of x plus c is going to give me absolute value of y. So absolute value of y equals e to the ln of the absolute value of x plus c, which I'm going to, again with a property of exponents, I'm going to write that as e to the absolute value of x times e to the c. I'm going to call this guy an a. And look at that, e to the absolute value of x. Oops, I missed the ln. E to the ln of the absolute value of x. E to the ln of the absolute value of x times e to the c. Well, e to the ln of the absolute value of x, since e and ln are inverses, that's just absolute value of x. So I can write this as y equals a absolute value of x. And again, that really indicates y equals plus or minus a absolute value of x, but that a is indeterminate so far. So whether it's a plus or minus, we don't know. So we'll just let it absorb that plus or minus. So here's our general solution. And if I wanted a particular solution, I would have had to have given you an initial condition. So basically, all the functions that you graph that have the form y equals a to the a absolute value of x are going to fit this slope field in some form, right? They're gonna this slope field represents all that entire family. If I said if I gave you an initial condition, I could say initial condition. Let's just say I decided y of 1 is equal to 2. Well, then we can solve by plugging 2 in for y and 1 in for x. So that implies that a is equal to 2. So therefore, my particular solution would be y equals 2, absolute value of x. And again, if you go graph that, y equals 2 absolute value of x is going to be this guy here. Right, so that's that member of that. That's one member of this entire family. Notice this justifies that the derivative is undefined whenever x is 0, because you've got that corner there. So all these absolute value graphs that you can create here, they're going to all have corners. They're all going to have corners at 0. So the derivative would not be defined. All right. So on the next slide, I'll just show you the entire family of or submembers of this family, so that you can see that they're all absolute value graphs whose orientation depends on that a value, whether it's positive or negative. So again, here you see some particular solutions, and depending on what your a value is, the absolute value graph will either be opening up or down. But you can see that the slope field surely captures the essence of these particular solutions.